Welcome to ECE 302. This is lecture 4.7 on Gaussian random variables. I'm Professor Stanley Chen. As you can see in this outline, we're now in the third section of the discussion of common random variables. We're going to learn the Gaussian random variable, or sometimes people call it the normal random variable. The Gaussian random variable is the most important random variables in our course, as well as many of the engineering as well as scientific problems. There are many issues about the Gaussian random variable which we want to explore. They have many nice properties, but there are also some questions that people tend to not pay attention to. We will try to address them as much as we can in today's lecture. The outline of today's lecture is divided into four parts. The first one is the definition of a Gaussian random variable. I'm going to show you a formula that might look a little bit complicated in the beginning. However, I would expect towards the end of this semester, you will be able to memorize this equation. And then the second topic that we're going to discuss will be the mean and variance. This is a once-in-a-lifetime exercise I need to walk you through because this is a very important thing to know how do we derive the mean and also the variance of a Gaussian random variable. And then the third thing is the skewness and kurtosis of a Gaussian random variable. These are actually the high-order moments of a Gaussian random variable. Now, of course, skewness and kurtosis, they are defined for any kinds of random variables, but then there's a reference point, which is the Gaussian is the reference point. I want to show you the usage of these two quantities in modern data science problems. The last thing that I want to discuss is the origin of Gaussian random variables. The origin of Gaussian random variable is almost always not being discussed in a lot of the undergraduate probability courses, but this is actually very important. If we ask, here is the bell shape. This is a very beautiful bell shape distribution. Have you ever wondered where does this bell shape thing come from? Okay, and we are using Gaussian random variables every day. Why are Gaussian random variables so popular? What makes it the most important random variable in data science? So knowing the origin of Gaussian random variables is important. So we are going to spend some time discussing this topic. All right, so without further ado, let's start our discussion. Let us begin by talking about the definition of a Gaussian random variable. To define a Gaussian random variable, of course, we need to define the probability density function, the PDF. The PDF of a Gaussian random variable is given by this formula. It's a little bit complicated formula at the first glance. However, after a few times of exercises, you will be able to memorize. Let me walk you through how you can memorize this equation. This is the PDF of Gaussian. It is a bell-shaped function, which is something that, of course, everyone knows. Because it is a bell-shaped function, it has to be an even function if you are not offsetting the center. Okay, so if it is centered at 0, it has to be an even function. This even function is governed by this term here. Your variable is x, and then there is a center point mu. Okay, so that would be your mu. And then this is e to the power minus something. Now, as long as you have e to the power minus something, it has to be exponentially decaying. Okay, it has to go down on one side of the mean, and then go down on the other side of the mean. So you have to go down. The spread of this distribution is given by this sigma. Sigma is the standard deviation, which also controls how fast or how slow. Now you can see that if I have a very big sigma, then of course my distribution will become flat. So this is a big sigma versus if I have a small sigma, of course it will be more concentrated in the mean. Okay, so that is the exponential part. And then now what is this? This is a constant. The constant is there to make sure that when you integrate that curve, the area under the curve will remain unity. So this is the PDF of the Gaussian random variable. It's not too difficult to memorize. You have x minus mu, okay, everything is a square, and then the standard deviation is a sigma square, and so the variance is a sigma square, so that's the variance. You have a square, so you want to divide by 2, so that it will just be the 2 sides of your sigma. Okay, and then you minus your e, and then you have some constants, and the next constant is just 1 over root of 2 pi sigma square. So now, as you can see, this is the Gaussian PDF, and it's controlled by 2 parameters. One is mu, the other one is sigma square. Sometimes we write Gaussian, but some people prefer to write this little n to denote it's a normal random variable. Normal or Gaussian, they are equivalent. Okay, so you have 2 parameters, one specifying the mean, the other one specifying the variance. So this is the Gaussian random variable. The shape of the Gaussian random variable is, of course, a bell shape. You can move around the mean, as I'm showing you in this diagram. You make the mean small or big, and you're just shifting the Gaussian random variable towards the right or towards the left. If you fix the mean equals to 0, and then if you change the standard deviation, of course you are going to stretch the Gaussian distribution. And note that the more you squeeze to the center, because the area under the curve remains 1, you will make it taller. Okay, so now you are making the standard deviation smaller and smaller as you go to the center. Okay, so let us try to derive some properties of the Gaussian random variable. In particular, we want to prove that the mean of the Gaussian random variable is indeed mu, and then the variance is indeed sigma square. Now you may wonder, isn't it just given by the picture already? The answer is that we have never actually proved that the mean and the variance they're mu and sigma square. The problem here is that I give you this PDF that asks, pretending that you don't know the mean is mu, the variance is sigma square. I ask, can you prove from the first principle that the expectation of this random variable is mu, and the variance of this random variable according to this PDF is sigma square? That is the question that we're trying to answer in this theorem. Okay. Now, as I mentioned, this is a once-in-a-lifetime exercise, and you need to do it once to make sure that you know what it is. And afterwards, you can just use this fact in your work. Okay. So, what is the expectation of x? The expectation of x, according to the definition, it will just be the integration of x times your PDF. Okay, so these two will will constitute a PDF of your Gaussian random variable. Now, you look at this integration. This is a super complicated integration. It is an integration involving x e to the power something. Okay, now let us take a look at this thing. The temptation is to do this integration by part, but if we can apply some tricks here, we can actually bypass this step. What we can do is that we can define a new variable y. Okay, y will equal to x minus mu. All right, and so of course dy will equals to dx. Then x will become a y plus mu. You just shift the mu to the left hand side. Then you have this equation here. So you have 1 over root 2 pi sigma square, and then you have this integration minus infinity to infinity of y e minus y square divided by 2 sigma square dy. Okay, that's the first part. And then you have the second part, which is 1 over root 2 pi sigma squared integration, and then you have mu, and then e minus y squared divided by 2 sigma squared dy, from minus infinity to infinity. Now the magic is here. This is 0. Okay, why? Well, this is 0 because the function here, this is an even function. You multiply this quantity, it becomes an odd function. It actually looks like this. If you integrate from minus infinity to infinity, that is 0. It's an odd function. How about this quantity? This quantity is mu. Why? The mu has nothing to do with your integration. You can pull it out. Okay? And then what? And then what you're integrating would be something here. This would integrate to 1 because you're integrating a PDF of a Gaussian random variable. No matter what it is, since it is a PDF, you have to integrate to 1. Okay? And so you have mu, and therefore the solution is mu. That's all. There's no integration by part involved. So this is the expectation of the Gaussian random variable. Okay. Now, how about the variance? The variance would involve a little bit more work, but that's still manageable. Okay. So it takes an integration by part once. At least it's not integration by part twice. Okay. Now let's look. The variance of x is this integration. Of course, you have this x minus mu squared, and then you multiply the PDF. I'm going to define y as what? As x minus mu divided by sigma. That is my substitution. If I put the substitution, I will have this sigma square. Okay, extra sigma square that goes to the numerator. Okay, so you can follow this expression because dy will equal to 1 over sigma and then dx. So you can put the equation in the right order, then you can see what is happening here. Okay, now once you land onto this expression, then you can see that this is y squared and e minus y squared divided by 2. If you do integration by part once, you can squeeze this term out, and then you have the other term that comes out. Now this term is 0. Why? Because when y is infinity, this term is decaying a lot faster than this y here, and so it will go to 0. When it is going to minus infinity, you have a square, so this is still going to 0. So no matter what happens, this is 0. How about this term? This term, the magic is here. This is integrating to 1. Why? This is the PDF of a Gaussian random variable. Okay, it's a unit variance, 0 mean Gaussian random variable. So if you integrate, you will get 1, and therefore you have sigma squared. Okay, so this theorem proves two very important results. The first one says that the mean is mu. The second one says that the variance is sigma squared. Okay, I'm going to introduce another Gaussian, which is the standard Gaussian. The standard Gaussian says that mu equals to 0 and then sigma equals to 1. It's also called the unit 0 mean unit variance Gaussian random variable. This thing it has a PDF given by this formula. You just substitute sigma equals to 1 and mu equals to 0. Now this standard Gaussian is a very useful thing for the following reason. Whenever you want to evaluate Gaussian random variable, you need to specify the mu and sigma. But with the standard Gaussian, because the mean is 0, standard deviation is 1, you can just specify the Gaussian in terms of this equation. Okay, and then when you have a new mean, you have a new sigma square, you can just put this into the same formula that I'm going to show you. Okay, instead of specifying mu equals to something, sigma equals to something. So this will give you a very easy notation in terms of expression the Gaussian. Now I'm going to define a term. It's called the CDF of a unit variance zero mean Gaussian. Is given by this phi function. This phi function is just as it's called, is the CDF. So we integrate this PDF function and got to this height. The area, of course, is integration from minus infinity up to x for this PDF. So that would be your phi function, okay, and that will give you to this height. Okay, so this is called the phi function. Phi of x is the CDF at x. Okay, and that's the CDF of a zero mean and then unit variance Gaussian. Okay, so as I'm defining here, the CDF of the standard Gaussian is defined as this phi function. Okay, so that's also the CDF of x, and it's given by this integration. This CDF is related to a very famous thing. It's called the error function. The error function is defined as this expression here. It's just a different endpoint in the limit, and also the scaling in the expression. And you can do a very simple one-to-one mapping from the CDF to the error function. Okay, so if you start with error function, you can get a CDF in this way. You start a CDF, you can get an error function in this way. So these are interchangeable in many settings. Okay, so now why do we want to talk about the standard Gaussian? The reason is that if you have any arbitrary Gaussian, then the CDF can be expressed in this. Right? This is a very easy notation. You have a standard Gaussian, and then you have something to put in. The standard deviation going into the bottom, and then the mean goes to here, and then you have x. This is the CDF at x for arbitrary mu and arbitrary sigma. Okay. Now, why is this true? Well, this is true. You can start by showing this. You can start by showing the CDF. The CDF is the integration, right? The integration from minus infinity to x of 1 over root 2 pi sigma square e minus t minus mu square divided by 2 sigma square dt. That is your CDF of x for an arbitrary mu and sigma. Now you can define a variable y equals to t minus mu divided by sigma. And so now if you integrate it up to x, if you do the substitution, this term will turn into y, and then the sigma square will be gone. So this is the PDF of the standard Gaussian. The only thing that changes would be this upper limit. The limit will become x minus mu divided by sigma. So this is going to give you phi of x minus mu divided by sigma. And so now you can see this is very, very handy. That is a CDF for an arbitrary Gaussian. We evaluate at some point. This is an expression for a standard Gaussian, but now because of this transformation, you can put in any arbitrary mu and sigma into this expression. You can get the same value. So on computer, you can just use the same Gaussian, the standard Gaussian, and then by shifting the x value and scaling the x value, you will be able to get to the exact same probability. There are other results which I will just briefly mention. This result says that if you have a random variable x which is a Gaussian, and it is between a and b, that's the interval that you're trying to evaluate the probability. This is the same as finding the CDF of this guy, the right hand side with this transformation, and then minus the right hand side. This is just because of the following reason. This is the probability of the interval. You have the upper limit minus the lower limit. You have these two CDF evaluated. These corollary results are also pretty easy to derive. I will just leave the derivation as an exercise. Okay, and I would really encourage you to try to prove that, or you can just draw a picture and see if you can derive these results. Okay. Now, I want to move on something that it may not be as obvious to some of you. it may be the first time you learn about this. This is the notion of skewness and kurtosis. Okay, for any random variable x, we can define the PDF, of course. We can also define the following central moments. Okay, the central moments, of course, is a variant of the moments. Moment just take the square, the cube, the fourth power of the random variable x. Central moment means that I'm going to subtract something. The first order central moment, of course, is the expectation. So that's pretty easy. The second order would be the variance. You just subtract subtract the mean. You take the square, you have the sigma square. The third order is called the skewness. This is called skewness. Okay, skewness is expectation of the thing to the power 3. Kurtosis is the thing taken to the power 4. Okay, so they're just the first order, second order, third order, fourth order expectations of the random variable. This applies to any random variable. But for Gaussian, there's something very interesting. Okay, for Gaussian, the skewness is always 0. The kurtosis, well, I'm going to define another term. The kurtosis for Gaussian is 3, but if you look at this offset, then it's called an excessive kurtosis, and that for Gaussian is always 0. So Gaussian has some very interesting properties for the skewness and kurtosis. Let me briefly talk about skewness. Okay, what is skewness? Skewness, of course, is defined by the third power of the expectation. Skewness measures how asymmetrical the distribution is. Let's look at this diagram here. This is a thing called the positive skewness. Okay, this is a thing called a negative skew. The positive skew and negative skew, they're just leaning towards either side of the distribution. If it is exactly symmetrical, the black curve, this is symmetrical, then you get 0 skewness. Now, a Gaussian, you can see that why Gaussian has a 0 skewness. The Gaussian is, just by definition, is a bell shape, is a symmetric function, and therefore it has skewness of 0. There are many distributions that you can find in practice that they will lean towards one side or the other. These distributions, they have a non-zero skewness. What is kurtosis? Kurtosis measures how heavy tail the distribution is. Okay, Gaussian has a kurtosis of 3, but some people prefer to define this thing called the excess kurtosis, which is this kappa minus 3. So you take the kurtosis minus 3, then Gaussian will have a kurtosis of 0. So what do I mean by heavy tail? You go to this diagram, you can see that a Gaussian has this. Okay, so that the black curve is a Gaussian. It has a kurtosis of 0, excess kurtosis of 0. Now, if you use this orange curve, then you have a lower tail. Okay, so this orange will have this 2.8. So it means that it will decay to 0 faster. If you go to the blue, this is a very heavy tail distribution. Then you have a kurtosis less than 0. So the kurtosis sort of measure how much of the energy that you will still have on the two ends. That's the tail distribution. More heavy tail distribution normally is harder to work with because you have probability to have outliers. Okay, so kurtosis is a metric to evaluate how spread the distribution is, how heavy tail the distribution is. The skewness and kurtosis for commonly used random variables are summarized in this table here. I'm not asking you to memorize any of these, but I just want to show you as a reference point. If you are ever working on a problem, you want to know the skewness and kurtosis, these are the formulas that you can use and verify. The interesting thing is this, that for the Gaussian, you have 0 skewness and also 0 excess kurtosis, which is the very, very nice property of a Gaussian. Okay? For other random variables, you may have some values. Here is a very practical example which I find from the internet. If you go to this website, thekaggle.com, you'll be able to find many useful data sets. Some people are even launching various competitions for data analysis, so you can try that. This is just one of the many examples. It's called a Titanic data set, where they are monitoring the number of survivors versus the number of died people in this accident. So there are various statistics that are reported in this data set. You can calculate the mean, you can calculate the standard deviation, you can calculate the skewness, you can calculate the excess kurtosis. The histogram of this data set, I took the data set and plotted the histogram. It looks like this. Okay, so that's group 1 and group 2, and then the x-axis is the age. Now you ask, are these two distributions different? It turns out that if you only look at the mean, you look at the standard deviation, it is almost impossible to tell whether the two distributions are similar or different, because they have similar mean values, they have similar standard deviation values, so it is very difficult to tell. But if you measure the skewness, you can see that one has a lot bigger skewness than the other. Okay, if you look at the excess kurtosis, one has positive and one has negative kurtosis. And so these high order moments actually buys you information in problems such as this, where the first two order moments, they are not that informative. And so I hope you can try to go to this website and download some of the data sets and play around these statistics and see if it helps you to solve any practical problems. Maybe some of these high order moments will be helpful. Okay, so now we go on to the most interesting question for today's lecture, which is where does this Gaussian bell-shaped function come from? Why are they so popular? Why do they have this bell shape? Okay, so we want to answer these questions which are typically not answered in the textbooks. So what is the origin of Gaussian? The origin of the Gaussian has to do with something called the central limit theorem. Okay, some people prefer not to mention that, but I think it is so critical that we have to know it. The reason that we are studying Gaussian is because for many of the practical systems, you do not just look at one single random variable. You have a lot of random variables and you're looking at the average, or you're looking at the sum. Okay. For example, you are measuring the electrons. The electron, you never look at one electron. You look at the voltage. The voltage is a collection of electrons. You look at data points. You're not just looking at one data point. You're looking at many data points. Sometimes you're looking at the average of these data points. The nature of the data collection process will force you to look at the average, a sum of some underlying or latent random variables. Whenever you do this summation, you enter this range of central limit theorem. Okay, and because you're doing the central limit theorem, you are convolving the PDFs. Let me show you one example in order to illustrate these points. Suppose you throw a dice. The dice has 6 faces. It's a fair dice. You throw the dice once. You draw the PDF. It is a uniform distribution. It's flat, almost flat. Okay. Now, if you throw the dice twice, you add the numbers up. Okay, so you have 1, 2, 3, 4, 5, 6. These are the 6 numbers. If you have the first dice, you have the second dice, you add the numbers up. I ask you, what is the distribution of x1 and x2? The distribution looks like this. It makes sense because it is more likely that you will get a 7. Why? Because you have 1, 2, 3, 4, 5, 6. You get 5, you get 2. Okay, the first dice is 5, the second dice is 2. You add them up, you get a 7. You can also get a 7 here. So you have it's a lot easier to get a 7 than getting a 2. To get a 2, you must have 1 and 1. Okay, and so the distribution of the sum is a triangle distribution. That makes sense. Okay, now if you continue the experiment, you have 5. Well, you're getting something like this. If you have 100, you get this distribution. This is a bell shape. Okay, it's a very, very surprising thing. When you add things up, when you add the random variables up, the PDF of the resulting distribution is becoming a bell-shaped curve. So what is happening? What is happening is this idea. We can think about the uniform distribution. This is a rectangle, and then there is another rectangle. You're going to get a triangle. What kind of operation that you need to do between a rectangle and a rectangle to get to a triangle? This operation is called a convolution. Okay, how does it work? Well, the convolution says that you have this rectangle here, and then you have the other rectangle, and then convolution will flip this rectangle over, and then try to overlap these two, and then try to integrate. Okay, so you're going to flip and then shift and then add. All right. So now, whenever you try to do this operation, it's called convolution operation. Something that that's very common in the undergraduate signal and system in textbook. So you do this convolution, and then in the beginning, you have very few overlaps. Okay, so in the beginning, you have just this tiny area that are overlapped. So you have a lower value. Okay, so that would be lower value. But towards the middle, you have a lot of overlaps. So here you have a lot of overlaps. So then you go up. When you have the maximum, when you have exact overlap. So that is the peak. And then afterwards, what would happen? Afterwards, the original rectangle is here, and then you move to the right, and so the overlap drops again. So that is the reason why we have this a triangle distribution when you're trying to convolve the two rectangle distributions. Now, if you're interested in knowing the definition of this convolution, the formula of the convolution is given by here, right? And that's easily accessible in most of the textbooks in undergraduate signal systems. So that's the convolution. Now you can imagine that is one random variable x, and then the other one variable x2. That's the PDF of the two random variables. You convolve them. Okay, that is equivalent to sum of xy is equivalent to fx and fy. Okay, so now you have 3, you have 4, you have 10, you have 100, you have 1,000. When you try to convolve these, what will happen? In the thing called the Fourier domain, so if you take the Fourier transform of all these convolutions, this is equivalent to taking the product of all these Fourier transforms of these PDFs. And so now each of those, each small fx, that is a rectangle. If you take the Fourier transform fx, this is going to give you a sinc function. Okay, a sinc function is defined as sin x divided by x. So you have a sinc function. Now, if you have many sinc functions, you multiply them together, you can actually turn on your Python MATLAB and see it will eventually converge to a bell-shaped function. Okay, that is just the nature of this problem. You multiply the sinc function infinitely many times because the sinc function has this ripple here. Okay, so the more times you multiply, these ripples, they're less than 1, so they will start to die off the more you multiply. So eventually it will become a bell-shaped function. And this bell-shaped function is a Gaussian function. The Gaussian function will take the inverse Fourier transform. You can prove that it remains a Gaussian function. Well, in other words, if you convolve the PDF infinitely many times, you will indeed get a function that has the Gaussian form. That's why you are getting Gaussian random variables by summing different random variables. And this principle actually applies to any PDF. It's not just a rectangle. It's not just a uniform distribution. It applies to any random variable. As long as they're independently added up, you will get this central limit theorem to work, and you will have a Gaussian. Now, of course, to prove the central limit theorem, I will discuss this in a later lecture when we have the opportunity to talk about that. But at the high level, what I really want you to know is that Gaussian doesn't come from the mass. The Gaussian comes from the fact that we're summing random variables. This is just part of the nature how we collect data. Okay, so what is the origin of the Gaussian? You get a Gaussian by summing random variables. What happens if you convolve the PDF infinitely many times? You will get a Gaussian, and this is known as the central limit theorem. Why are Gaussians everywhere? We seldom look at individual random variables. We often look at the sum and average. And whenever you look at the sum, the central limit theorem kicks in. And if you try to sum, it's equivalent to do this convolution. Okay. There are a couple of things that we have not talked about. Okay. One is the meaning of central limit theorem. As I said, we will discuss in a later lecture. The other thing that we haven't talked about is why summing two random variables is equivalent to a convolution. I'll show you an example, but I haven't mathematically proved that. We will also do this in a later lecture. But if you agree with our argument here, then I hope you can see that why Gaussian is so useful. It is useful because you sum. It becomes a Gaussian because you convolve. Whenever you convolve many functions together and they are identical, you will eventually get the bell-shaped Gaussian distribution. All right. So I hope this lecture has given you some very useful information. Hopefully some of those are new to you, and I hope that you will not just treat Gaussian random variables as yet another random variable. It is the most useful random variable because of several reasons. We have gone through the derivations of the mean and the variance. We've talked about the high order moments, how they can be useful in data analysis. We've also talked about the origin of Gaussian random variables. These are very useful things to note about the Gaussian random variable. I hope you have enjoyed this lecture. If you have any question, please send me an email or post your question on our Piazza forum. And for Purdue students, I really encourage you to work on homework problems. You may have difficulty, but don't worry. Just let us know. We'll be very happy to help you out. Thank you very much for watching. I hope to see you again next time.